Welcome to homework.
Okay, so for this problem, we have an electron in a field, and then the field is being turned down, and we're asked what's going on with the motion, what's the acceleration of the electron at the instant, um, or the instantaneous acceleration if it's at these particular positions. So we have at the center, above the center, and below the center. So let me go ahead and properly label those. So above it was C, middle is B, and then below it is A. And so let's figure out why exactly it's moving first. So we know that it's responding to an electric field. So generically, the Lorentz force is F is QV cross B plus QE, but there's no initial velocity that we know of, so that we just need to worry about QE. So now we need to know what's the electric field. So we can use the full form of Faraday's law to do the line integral around some, I don't know if they call it a Faraday surface or something. So let's say for either A or C, we do E times 2 pi r is equal to the flux, so B times pi r squared. And then doing the math on that, you got E is 1/2. Oh, sorry, it's the derivative of this, so dB dt. So that's 1/2 dB dt times r. I kind of glossed over this. Hopefully there's some similar examples, but in the book, let me see if I can find any offhand, because I know I kind of just said that. But let me see if I can point you to like a good resource to feel motivated that that's true. Was Faraday's Law a different chapter than this? Oh, it must have been a different chapter. Okay, well, I guess it doesn't really make sense to give like a full-on introduction, but I know we haven't really used this equation much, but it's in one of the earlier chapters on Faraday's Law. And so anyway, so that's our electric field, and then F is QE, and then of course we want acceleration, so it's MA. So let me quickly do that. A is equal to QE over M. And now we have our E, so therefore we can say the magnitude of the acceleration. I'll talk about signs in a second. Let's just talk about magnitudes right now. So a lot of these, I guess, are magnitudes. So let's see, kind of stick them all there. Wow, kind of going overboard. Okay, anyway, this is Q over M. So I'm just combining these two formulas. Q over M times E times 1/2 times R times dB dt. Okay. So let's think about which direction the electron is going to accelerate. So let's first figure out what direction the electric field is. So we know that the field is going into the page. Or did I just draw X's like that? Let me just double check. Oh, yes. Yeah. B is into the page and it's decreasing. And so if it's decreasing, that's going to make an EMF. So if it's into the page and decreasing, it wants to keep it into the page. So it's going to create an EMF, which would cause a current to go this way. So the electric field here is like that, and then the electric field from the bottom is like that. But electrons go in the opposite direction of the electric field, so then we can say the acceleration is the opposite direction. And so so we can say this is the magnitude of the acceleration. And by the way, the acceleration for A and C is equal and opposite magnitude. So this is kind of a representation of the acceleration at C, and this would be A. And then for B, you're sort of, I don't know what they call the surfaces, but like your analog of your Gaussian surface, like your loop would have a 0 radius. So there's no electric field at B. So I'll just kind of succinctly write that. A at B equals 0. And then the acceleration at C and A has equal magnitude but opposite direction. So let's figure out what the actual magnitude of the acceleration is. When I calculated it, I got 4.4 times 10 to the 7. Let's make sure I have all the givens written out. I actually pretty sure I don't. I don't think I have any of them. So let's see, the radius is 0.05 meters because it's 5 centimeters, and dB dt is minus 10 times 10 to the minus 3 Teslas per second. And are there any other givens? No, well, Q is the elementary charge of electron, 1.6, 10 to the minus 19. Mass is 9.11 times 10 to the minus 31. So plugging all that in, I got 4.4 times 10 to the 7 meters per second squared. And then I would say for C, the acceleration is to the right. So let me look at what coordinate system this problem's using. So I would say it's 4.4 times 10 to the 7 in the x hat. And then for oh wait, that would be in the negative x hat. Let me double check my picture. C is on the top, A is on the bottom. I'm getting something. It's not quite checking out. Let me double check. Okay, so it is an electron, right? So I'm just gonna look back through my reasoning. So my answer's not meshing up with a different answer. So the field is into the page, it's decreasing, and so in magnitude, and so an electric field will create a potential that would accelerate an atom or a positive charge in the clockwise direction, which would create a field into the page to compensate for the decreasing field. So then I would say I would stand by my electric fields this way, and then the force is in the opposite direction of an electric field for a charge. So okay, I do, I guess, stick by this answer. Okay, so for A, it's minus 4.4 times 10 to the 7 in the x hat. So A would be, oh, it is right. Okay, A would be to the right, and then C would be to the left. Okay, that actually does mesh with the other answer. Great. So I'll just like circle the answers because I kind of did this in a sort of nonlinear way, but it's okay. So here's my kind of blobs of answers. Blob, blob, blob.